introduce
Yep.
Dr. Sangwine from Essex University ですけれど、実は先週 ICU で、
Wrong. Yes.
ICU で、レクチャーをやったんですけれども、YouTube に上げる用のビデオを取り損ねたということで、もう一度撮り直しをやるという。で、せっかくなので、工学院大学に来ていただいて、お話をしてくれると。で、title of his talk is Color Image Processing with Hypercomplex Algebra。複素数はコンプレックスナンバーですけれど、それの超複素数ということですね。ハイパー、超複素数代数のを使った色画像処理というタイトルで日本語で言うとそうなります。イングリッシュで適宜ですけれど、適宜日本語でもいいので分かんないことがあったら誰かが訳してくれます。はい、じゃあよろしくお願いします。Please.
Thank you. Okay. Let's go directly to yes, that's better. This is a very good projector here. Okay, so this talk is really in two parts. It takes some time to explain the first part, which is a brief overview of colour science, because that enables us to make sense of what comes afterwards. And I'm talk about quaternions and quaternion Fourier transforms, which are things I've worked on for 15 years or more, and particularly the interpretation of quaternion spectral coefficients. That is, what does the quaternion Fourier transform represent about a colour image? How does it represent the information that is in the colour image? And towards the end, I'll just have one slide to briefly mention Clifford algebras. Okay, so I've aimed this part of the talk at somebody who is technical but is not aware in detail about how colour works, because this is not a simple subject. This man was an Englishman, famous man, who made the first steps in understanding colour science in 1666, which was a year that most of London burned down. That he showed in this famous experiment, indicated by this prism picture, that you could split white light into the colours of the rainbow. And also, if you place another prism suitably arranged, you could combine the colours back into white light. So he showed that white light was composed of many colours of light. However, while it is true to say that each wavelength in the visible spectrum has a colour, it is not true to say that colour is associated with wavelength. Okay, it's a one-way relation. Every wavelength has a colour of visible light. But the colours we see with our eyes are not generated by pure wavelengths. We see light which is reflected from objects, and objects have a surface chemistry which determines the colour and the wavelengths that they reflect. Okay, so whether it's a natural material or a synthetic material like the fabric on these chairs in here, or the green on that blackboard or whiteboard, paint on the doors, clothing, all these are chemical materials and they reflect light according to their chemistry. And so we can immediately see that colour is a property of a reflecting surface. And this is made very clear in this diagram, which I took from Wikipedia, because it shows reflectance of metal mirrors, polished samples of aluminium, gold and silver. And it shows for each wavelength the percentage of the incident light on the mirror which is reflected. And you can see immediately why gold appears the colour that it does, orange and yellow colour, whereas aluminium appears almost neutral, very silvery, and silver has something in between. So gold appears orangey yellow because it absorbs some of the wavelengths and doesn't reflect everything. And in general, that's very clear for polished metal, but in general the same applies for other materials. So fabrics, paint, natural materials reflect some wavelengths more strongly than others, and they absorb some wavelengths more strongly than others. And that gives the colour that we describe as belonging to an object. So the colour that we see is dependent on the whole spectrum of visible wavelengths reflected from a surface. And, well, I should say also that it depends on the incident light, because the wavelengths reflected can only be dependent on the wavelengths which are incident on a surface, and so the colour of a surface is affected by the colour of the light that illuminates the surface. Now, metamerism is what makes possible computer displays, and it makes possible printing and all sorts of other technologies, because this is the key to reproducing colour. These are two statements about metamerism. Okay, the first one says you can have two surfaces which appear the same colour to a given observer under the correct illumination. So let us say we choose daylight, natural daylight, and we can make two surfaces which appear the same colour even though they're made of different materials. So one might be a plant, and the other might be a painting of a plant with paint representing the colour of the leaves on the plant. And what version number 1 there says, the paint that we use to paint a painting of a leaf doesn't have to be made of the same material as the leaf, and it doesn't have to reflect the same spectrum. It simply has to reflect a spectrum which appears the same colour. The second statement is very important for projector displays, computer displays, digital photography, analog photography using film and photographic paper, because what that says is you can reproduce the colours that you see with your eyes using photographic materials and computer displays. And again, they don't have to reproduce the same spectrum, they just have to reproduce the same colour, which is a very important property, because otherwise we would not be able to have colour photography or colour displays. So, these two statements about metamerism explain why we're able to have electronic displays, photographic film, ink on paper, reproducing apparently natural colours. And the material that reproduces the colour doesn't have to reproduce the same spectrum as the original object. It's enough to make a spectrum which is perceived to be the same colour. That is, human observers looking at it say, yes, that's the same colour. Now, another aspect of human colour vision is this thing called trichromacy, which is essentially based on the fact that inside the eye, the retina has 3 types of cone that respond to light of different wavelengths, and these are essentially colour bands of roughly red, green and blue, but the key thing about this is that human colour vision is trichromatic, so we see in 3 bands of colour. And I have here an example to explain this. Okay, are you familiar with this film? You've seen it? Yeah. Okay. Avatar, yeah. So you know the story, but I'll just briefly explain it for the purpose of people watching this on video. This film is a science fiction film set on a moon orbiting a gas giant of a distant star system. Well, not so distant, it's about 6 years away from Earth by light speed travel. And there are alien humanoids living on this planet, of whom the one on the left is one of them. And the humans have gone to the planet to mine a mineral, and the character on the left is, remember this is science fiction, it's not reality, the character on the left is a humanoid body, synthetic humanoid body, inhabited by a human mind. The human character controlling that body is lying in a box somewhere, wired up to a lot of something, electronics or whatever it is, and he's thinking and controlling that body. So he's inhabiting the body by remote control. So my caption there shows that, and this of course is not a line from the film. The film, they completely ignore this aspect of the film, as they ignore many things in science fiction. He's saying to Neytiri on the left, "Oh, this is weird, the colours don't look right to me." And of course he would, because the body he's inhabiting is not a human body. It doesn't have human retinas in the eye. The brain system is different, and it's highly unlikely he would see the same colours that he would in his human body. And so he's really puzzled, and I think her facial expression captures, something about him. What's wrong, Jake? What's the problem? So, if we were to meet aliens, it's quite likely we cannot talk to them about colour. It's a human characteristic, something in our perception. Okay, so it's not like mass, it's not like temperature or voltage, where we could, once we'd figured out how to talk to aliens, or they'd learned to talk to us, we could compare things. We could present them with a kilogram of platinum. So this is a piece of platinum, and we call this 1 kilogram. It's our unit of mass. And they could weigh it or analyse it and work out the equivalence. We could do the same with temperature, voltage. Give them a voltage source and say this is 10 volts electrical. So what do you call that? And they say, okay, well, we have a different unit, blah blah. Now, we don't even have to think about aliens in order to imagine this human vision problem, because other species on Earth have different forms of colour vision, or don't see in colour at all. And this is known from experiments and experiments similar to the ones done with humans, where you get animals to behave in a certain way according to colour stimuli. So we know that insects can see ultraviolet light. Some species have monochromatic, tetrachromatic or pentachromatic vision. So there are some animal species that see vastly more detailed colour pictures than we do, and other animals that see less. And of course it's worth mentioning that not all humans see colour in the same way. Our computer displays are designed for the typical average human, but those with abnormal colour vision find it difficult to use normal computer displays because they can't distinguish, for example, red and green. Now, another observation, and colour science has grown up over the last 150 years from observations made with human subjects doing experiments in darkened rooms. And what has been observed and is well understood is that humans see two opponent colour systems. Humans will place red and green at opposite ends of a scale, and they'll place blue and yellow at opposite ends of another scale, and these are orthogonal, they're independent of each other. And you know this in a way because if you try to imagine a colour that's reddish-green, you can't, because it's like saying, imagine a cup of hot and cold coffee. It's not possible. A cup of coffee has to be hot or cold, or somewhere in between, and you cannot say there's a point where it's both hot and cold at the same time. Same with blue and yellow. So I made a diagram to show this. To some extent, it's a little difficult to depict it, but the red-green scale is shown horizontally, and the blue-yellow vertically. And in the blue-yellow case, you go through a neutral grey value in between. These are the sort of primary colours of the visual system, and then there are secondary colours which we can put in like that. So midway between blue and red we have something called magenta, midway between green and blue, cyan. So that's the human opponent colour system in a picture. So we can see, if we want to measure colour, and there are many reasons why colour needs to be measured. In particular, if you think of technical applications, you need a number. You want to order some paint, you need to specify the colour of the paint, and it needs to be done with numbers. And so we need two numbers to characterise a colour. You cannot do it with a single number. And these two numbers are called chromaticity. And normally they're between 0 and 1. So they're like XY coordinates on an XY diagram. And they enable you to specify the colour of a surface, a paint, or a light. And this diagram shows the chromaticity coordinates and all the possible chromaticities. And you'll see there's a curved perimeter there, which corresponds to the colours of the rainbow, pure wavelengths of light. And that's the curved perimeter that starts at the bottom left and goes up to the top left and then comes round to sort of right below, just below centre. And the colours on the diagram there give you a rough idea what those chromaticities are like. Now, inside that shape, those colours do not correspond to single wavelengths. They must be made by mixing together different wavelengths of light. And a simple way to do that is to mix together 2 or 3 colours. But if you choose 2 colours and mix them, you can only produce colours which lie on a straight line between the 2 colours. Whereas if you choose 3, because human colour vision is trichromatic, you can mix 3 colours together to produce any colour inside the triangle. Which means if you're going to design a display system to use 3 colours, you want to choose a triangle of colours as widely spaced as possible. Okay, so ideally you'd want something like 3 lasers or 3 light-emitting diode displays that would give you wavelengths widely spaced on that perimeter. Of course, with projectors, it's not so easy to do that, and often you have to compromise and have a triangle which is somewhere inside that diagram. Notice in the middle you get white. If you combine colours in a suitable combination, you get white, which with something else that we're going to see in a moment enables you to produce shades of grey, because grey is simply a darker version of white, as we'll see. Now, colour reproduction for electronics was devised in the 1950s when the first colour television systems were created, and the same system has carried on to be used in computer displays, digital cameras, smartphones. They all use the same system. And this picture shows a breakdown of a colour image into a luminance component, which is on the bottom left. That's what we normally call in English black and white, or a monochrome image. And chrominance, which is shown on the right, which is the, like we just described, adding the chrominance is sort of representation of the chromaticity. It's an electronic aspect of the chromaticity. And you see there what it looks like. I've displayed it there with flat luminance. So it's the colour aspect of the picture with no variation in brightness. And when you combine the luminance variation in brightness with the chrominance, you get the full colour picture. So in informal terms, luminance is what we call black and white. Chrominance is what you need to add to the luminance to give a full colour result. And the chrominance part of a colour image is, or a video is related to chromaticity. Now, how is colour represented electronically? As I said in the previous slide, it was devised in the 1950s. It's remained fairly standard ever since. There have been a few technical changes, chiefly because the United States and Europe use different colour primaries for the two different television systems, and we've now more or less converged on a standard system which is used in our computers and smartphones and digital cameras. And the system is called red, green, blue. It uses a red, green and blue primary, and they're combined to make all the colours that we need on our displays. And here we see what the red, green, blue aspects of an image look like, then what they look like combined to make the full colour image. Okay, so this is how colour is represented in digital pictures and digital video, largely speaking. Okay, because we've got 3 channels, the range of possible digital values in a colour image can be represented in a cube. So we've got 3 coordinates, 3-dimensional space, and we call this the RGB cube. And typically it runs from 0 to 1 along each coordinate, and the vertices of the cube are black and white. The origin is black, furthest from the origin is white. The 3 primary axes, red, green and blue, the maximum extent of those, and then the other 3 vertices are magenta, cyan and yellow, which are combinations of the primaries taken 2 at a time. Okay, now we move to, having explained colour science, we move on a little to the second part of the talk, which is to explain Quaternion Fourier transforms and why we use quaternions to represent colour images. And the key thing here is to think of pixel values in a colour image as vectors. Okay, so each point in the image is represented digitally by 3 coordinate values in the RGB space, and we think of those 3 coordinate values in the RGB space as a position vector in RGB space. What we want to do is manipulate those position vectors geometrically using a suitable algebra. We want to treat the vectors like numbers. We want to be able to do addition, subtraction, multiplication, maybe division, and manipulate them in the 3D RGB space. And for the last 15 years or more, I've done that using quaternions, which are 4-dimensional hypercomplex numbers discovered by Hamilton. But we could, in principle, use other algebras. We could use geometric algebras, Clifford algebras, for the same purpose. Now, the quaternions, they were discovered by this Irish mathematician, Sir William Rowan Hamilton, in 1843. Some people say this was the worst thing he ever discovered. Others think it's the greatest. But, you know, whether you like it or not, mathematics is there to be discovered, and you can't argue with the fact of the mathematics. The great thing I think about the quaternions was Hamilton made the first step away from real and complex numbers. He made the first step towards higher dimensional algebras, which opened the door for Clifford and others later to generalise to full geometric algebras. And it was a very difficult first step for anybody to make. What Hamilton was trying to do was generalise the complex numbers to 3 dimensions. So he wanted to have a number of the form a plus ib plus bit jc, for example, in 3 dimensions, and he failed because he was looking for certain properties in his algebra. And finally, he solved the problem by going to 4 dimensions. Okay, so he summed up his discovery in this famous formula, which defines the multiplication rules for multiplying these 4-dimensional hypercomplex numbers. So now we've got a hypercomplex number of the form a plus ib plus jc plus kd, 4 components, 3 of them in the imaginary part, and then those multiplication rules show how you combine ij and k. And as I said, it opened up mathematics to the discovery of other algebras. The Plutonians, which are 8-dimensional, followed very quickly from the discovery of the Quaternions, and then later the Clifford algebras, and then mathematicians have never stopped. They've gone on to infinite dimensions. So, Quaternion Fourier transforms. In 1996, I started working on this, and what I wanted to do was use quaternions to define the Fourier transform of a colour image. And the key idea was to have one Quaternion Fourier transform, one Fourier spectrum to represent the whole image, holistically, that is, as a whole, all in one. And it didn't take too long to find out how to define and compute the transform, but it did take quite a long time to understand how the spectrum represents the image. And essentially, the two pictures there give you the idea that we know that Fourier transforms represent signals or images in terms of sinusoids, and you can imagine, in the case of a colour image, colour sinusoids. So the striped picture on the right shows an image constructed from sinusoids varying between green and magenta. So oscillating between the two extremes of the colour cube, between green and magenta, sinusoidally. Okay, so we might imagine that a striped image like that would be fairly simply represented in the Quaternion Fourier transform, if we do the job correctly. So let's have a look at what these look like. Subsequent to the work that I've done on this, and I've done with a number of other people, we discovered that actually some people were ahead of us in this. Back in the 1980s, there were some two-dimensional Fourier transforms using quaternions. I've given the references up there. And this is shown as an integral notation. Of course, when we're computing with colour images, we work with discrete summations, but the formula is the same. And what you see here is a signal function f, which, because this is nuclear magnetic resonance imaging, it's a function of 2 time variables, 2 exponentials, each of which is in a different, has a different quaternion root of -1, I and j, but it could be other choices. And then, of course, the transform on the left, f of omega 1, omega 2, is going to be a quaternion function of omega 1 and omega 2. Then I based my early work in 1996 on the work of Todd, who in his thesis in 1992 gave this form of a two-dimensional Quaternion Fourier transform in which the 2 exponentials are placed to the left and the right of the signal function. Todd also imagined this with 2 time variables. He hadn't thought about actual applications. That was where I came in and thought, well, I could put f there as a colour image, where instead of t1 and t2, we'd have x and y, horizontal and vertical coordinates within the image. But again, the 2 exponentials have I and j as the square roots of -1. And that was the transform that I implemented in 1996, the first time I calculated the Quaternion Fourier transform of a colour image and successfully inverted it and realised I've got a way of handling colour images as a whole. And I've given some references there to others who followed that style. 2 years later, however, working with Todd, who by that time I'd made contact with, we came up with a one-sided transform. We realised 2 steps here. One, we could use a general root of -1. Okay, so in the quaternions, although there are 3 roots of -1, I, j, and k, in fact, they can be combined in linear combinations. So any unit quaternion with 0 in the first component, the A component, what's called the real part or the scalar part, is going to be a square root of -1. And they're actually points on the surface of a sphere, geometrically speaking. There's an infinite number of them, and mu here represents one of those. So we can make a choice of the square root of -1 in the exponential. Okay, we could do that with a two-sided transform. We could also then, a two-dimensional transform, but we could also, using an arbitrary root of -1, have a single exponential, a one-dimensional signal, and define a quaternion Fourier transform of a one-dimensional signal, which until then nobody had thought of doing. So we could have now a quaternion valued time series and compute a Fourier transform. Okay, so I've got a movie to show you. I made this in 2002, so 4 years after I'd first done a Fourier transform. And what it shows is a breakdown of that image into Fourier components. Starting at the very lowest frequencies, it gradually adds the frequencies into the picture. So, hold on, I have to just give the computer permission to open the movie. And it should come up in QuickTime Player. Yeah, let me just go to a larger size and switch it to loop so you can see it go round, and then I'll set it running. It will go around again, so you'll have another chance to see what happens. So after the title picture, the first picture you see is just pink, orangey pink, and that represents the low frequency component, the DC component of that picture. Then as you see some shape appear, those are the first few horizontal and vertical frequencies with 1, 2, 3, 4 cycles across the picture and vertically. Okay, so you see some shape begin to emerge as we add together the first few of the low frequencies, and then as higher and higher frequencies are added in to the picture, the image converges to the full detail image that you see on the title slide. So now we get a view of what the Fourier transform is doing, how it's decomposing this image into frequency components and representing them as a whole. We're not doing this in separate red, green and blue components. Right, so I'll stop that there. And to get back to there. That's it. Let's just go back. Yeah, and check I'm on the right slide. So, the question then is, what do the Fourier spectral coefficients represent? We've got this. When we compute the Fourier transform of the colour image, we have an array of quaternion values. How do they represent the frequencies in the image? And there are many ways of formulating the Fourier transform, and people who have worked on Clifford algebras have found many ways of formulating Clifford Fourier transform. So this question is one that will occur again and again with different types of transform. And to understand the issue, you need to know how the coefficients of a Fourier spectrum represent a signal or image, fundamental in all cases. So I'll give an explanation based on the classical complex Fourier transform, which very few people think about, because most people are working with real valued data and converting to a complex Fourier transform, but they're not working with complex data, complex signals or images. So what I've got here is classical complex Fourier transform, not Quaternion. This is just a classical complex Fourier transform that's been around since the 1960s. And what I did was I've taken a pair of complex exponentials, the same frequency, one positive, one negative. I've scaled each one with a complex number with randomly chosen amplitude and random phase. And they're shown in a polar plot on the diagram on the left, which is a little bit faint, but if you look carefully there, you can see two circles that just indicate where they are with the arrow. No, I've got this. Let me go back a step, sorry. There's one there, and the outer one is about there. And when you combine them, and remember they're going in opposite directions, one is rotating clockwise and one anti-clockwise. When you add them together, you get an ellipse, which is shown there in blue. Over here on the three-dimensional plot, it's easier to see in some ways. The three-dimensional plot shows a time axis, if you like, receding away from us, there, from 0 to 1200. And then perpendicular to that time axis is a complex plane. So what you're seeing there is a stack of complex planes going away from us, and the signal evolves through each one of the complex planes. Now, the two complex exponentials, which are recreated by the Fourier transform, one represents a clockwise helix and the other represents an anti-clockwise helix. But of course I chose random phase and amplitude for them. When you add them together, you get the blue signal, which is shown there. Okay, so that's an ellipse, a sort of elliptical helix, which is combined from those two frequencies. And that's fundamentally what goes on with a complex Fourier transform. The second slide shows a different case. Same thing, different random amplitude, different random phase, and you see now we get a different signal. This time the two combine to produce a very narrow ellipse. So we get an oscillation which is almost in a plane, shown in blue, but seen end on in the polar plot, there's a very thin, narrow ellipse. Okay, so that's the complex case. Now what I show you is, in hypercomplex Fourier transforms, something similar has to work. The Quaternion Fourier transform operates in a very similar way to that. Each Quaternion spectral coefficient encodes a circular path in 4 dimensions. However, it is confined to a plane. It doesn't oscillate arbitrarily in 4 dimensions. It is confined to a 2-dimensional plane. And when you add oscillations in 2 planes, you get an elliptical path in 4 dimensions, and again it's confined to a plane. And this is what it looks like. Okay, if we take an image, this is the Lena image, which is the one you saw in the movie, and because it's a 2-dimensional image, at each frequency in the image we have 4 spectral coefficients. We can have a horizontal frequency and a vertical frequency, and they can be combined, positive and negative. So we get 4 coefficients, and those 4 coefficients produce 4 circular paths in RGB space. So the plot on the left is RGB space. The 4 circular paths created by the exponentials sum together to produce that elaborate path in RGB colour space. So at a given frequency, we're looking at some kind of complex path in 3 dimensions in this case, because we're reconstructing the colour image. Here's another example. Well, there's the Lena image, in fact. That's the 4 pictures there show those 4 oscillations in horizontal, vertical, and so on combinations. Right. Here's another example. This is the Peppers image. Different colours, different circles, but again an ellipse. And that's what the Peppers image looks like, and that's what those 4 frequency components look like. So we're breaking down the colour image into oscillations in RGB space around it, circular paths which combine to produce elliptical paths. And last year I considered whether this applies in other dimensions, because people are using Clifford transforms and they want to know, I'd like to know, whether this same problem occurs and how do we describe oscillations in higher dimensions. So I considered the problem of a signal oscillating in an arbitrary number of dimensions n in order to understand how hypercomplex Fourier transforms represent such a signal. And I came up with this result, which is quite surprising, I think. Any oscillation at a single frequency in n dimensions consists of an elliptical path in a plane. I've got a demonstration video which is in 3 dimensions because we can show the graphics in 3 dimensions, but let me emphasize this applies in any number of dimensions. 7, 27, 39 dimensions, the oscillation is always going to be around an elliptical path in a plane. That is, if the oscillation is at a single frequency. And in the video, what I've done is sum together a number of vectors in 3 dimensions, all oscillating sinusoidally in magnitude. So if you imagine a vector pointing out along a direction, oscillating in magnitude with a sinusoidal waveform, with an arbitrary amplitude, an arbitrary direction in space, and an arbitrary initial phase. And then I've combined a number of these together with the one common factor, they're all oscillating at the same frequency. And the result is always an ellipse. Okay, so let's have a look at this video. And again, let me just switch it to a larger display. And loop it for you so that it will play around several times. Okay, before I start, I'll just explain the grey vector there. Oh, let me just run it. Actually, it would be better and talk over as it runs. The grey vector is the resultant, and the ones that you see in colour are added together to produce the grey one. And you'll see, starting at the centre, there's a small green vector which is pointing sort of that way, oscillate. Of course, when the sinusoid goes negative, the vector points in the opposite direction. But the vector is always pointing along the same line. The red one is coming sort of out towards the front there, but it's again growing in amplitude. Then there's a cyan vector added to the end of the red one, and a yellow and a magenta vector added to the end of that. And so you see, you get an elliptical path in a plane, even though I've combined here, I think it's 1, 2, 3, 4, 5 vectors, all oscillating at the same frequency. And every time I run this, I get different random vectors chosen, but always an ellipse. Different ellipse, of course, because if you choose different random vectors, when they add together, you end up with an ellipse in a different plane with a different aspect ratio. But it's always oscillating at the same frequency. So this, I think, is quite surprising. Let me stop that. Go back to here. So, no, let's go back here a step. Oscillation in n dimensions at single frequency is always confined to a plane for n greater than 1. Okay, and this is really, you could take this as a description of oscillations of a vector signal, but it's also true of simple harmonic motion, because that's what this is. So if you have simple harmonic motion in 9 dimensions at a single frequency, being simple harmonic motion, it must be an oscillation in a plane. So all the Fourier transforms that anybody can devise, hypercomplex, higher dimensional, however they're done, they're always going to represent oscillation in a plane for each given frequency. Okay, so final thing to say is about Clifford algebras. Clifford algebras are a family of hypercomplex algebras. They include, well, I didn't mention there, the real numbers, of course, the complex numbers, the quaternions, but many others. Every algebra has a power of 2 dimension, so the elements of the algebra are either 2, 4, 8, 16, 32 dimensional or more. And the lower order algebras have dimension 2. And there have been many people working on Clifford Fourier transforms. And that analysis that I just showed you with the video works even in all of these algebras in any number of dimensions n. So, the conclusion. Colour is a human characteristic. It's a perceptual characteristic. It's not something physical like mass or temperature. And the way we represent colour in computers is based on 3 channels, which we can regard as the components of a vector in 3-dimensional space. And that's why I'm interested in using hypercomplex Fourier transforms to represent those images or signals with 3-dimensional samples. And I've shown you that the Quaternion coefficients in the Fourier spectrum modify a hypercomplex exponential to produce elliptical paths in 3 or 4-dimensional space. And this generalizes to any number of dimensions, so an oscillation at a single frequency always takes the form of an elliptical path in the signal space, always confined to a plane. And so any Fourier transform in n dimensions must represent these elliptical planar paths. And I've got a list of bibliography items which people can see if they have access to the full slides. I'll just go briefly through those for the video. Of course, people watching the video can freeze the frame and capture those. And I've just mentioned, of course, I didn't do all this on my own. I've worked with a number of people over the years. I'm still working with Todd, still working with Nicolas. Also work with Eckhard, who is behind the camera there. And there have been a few funding sources for some of this, including a grant, which I didn't mention there, which enabled me to come to Tokyo for these 2 weeks. So thank you very much for listening, and happy to answer some questions if you have some.
Okay, I ask the first question because then it's easier to ask the next question. Because every direction in quaternions expresses a color, and the unit quaternions.
I'm correct.
Yeah. The unit quaternions, they are on a sphere.
Yes.
So basically, every point on the sphere is one color. Because it is one color axis.
Yes.
So
remember, quaternions are 4-dimensional. RGB color is only 3-dimensional.
Yeah. So excluding the scalar part.
What it means is when we compute the Quaternion Fourier transform of a color image, we set the scalar part to 0, and so the resulting Fourier spectrum has certain properties which are special. That is, when we invert the Fourier spectrum, the scalar part comes out 0, because we started with 0 there. So we have certain symmetry properties in the Fourier spectrum which require the scalar part to be 0 when we invert. Okay, so, but it's then subject to that proviso, the pure quaternion with a 0 scalar part represents a direction in RGB space. So a unit pure quaternion represents a direction in RGB space, which would correspond to a colour. But it makes a difference where you place the origin. Okay, so the value of the quaternions in the spectrum is influenced by where we place the origin of the coordinate system, which is something I didn't realise until about 2004. It helps to put the origin of the coordinate system not at 0, 0, 0 black in RGB space, but in the middle of the cube, at the middle point on the grey axis. And that then would mean that your statement about every unit pure quaternion as a colour would be strictly correct. Okay, because in that case, the position vectors represented by the pure quaternions are pointing outwards from the centre of the RGB cube. and therefore they do point to one particular colour. If you have a black-centred coordinate system, it's much harder to interpret. Shifting the origin, in fact, is non-linear operation, but it's a trivial thing to do. So it helps to convert the colour image into the grey-centred coordinate system, as we call it, do the Fourier transform work and so on, and then convert back at the end. It's a trivial step, just adds a value or subtracts a value from every pixel.
So I wonder if it would be a meaningful representation to show sphere in 3D, which shows periodic quaternions, and to give a color value
yes,
to
yes,
every
I've done that.
pixel
Yes.
on sphere, and then
I have done that.
the people see this, they can immediately
Yes.
this is meaning.
Yes, indeed.
Yeah.
In fact, that's what was happening in those elliptical path plots. The points plotted in the elliptical paths were coloured according to the direction the vectors were pointing. But yes, you're right, it's quite easy to produce a sphere coloured in that way. I can do that.